Thank you. My name is Mark T. Sopkel. I am also, among other things, a financial chair for this conference. But my regular day job is for the Harvard Hughes Medical Institute at Virginia Research Campus, where I'm a software engineer. This is the second half of the Simone Byrne Hour. As you can see, Simone is also a major contributor to HDF5. And HDF5 development and maintenance is led by Mustafa Mohammed, who unfortunately could not be here today. So I have the honor of presenting about this package. And I'm going to get start with a few slides, and at the end, we'll come back to Simon. So what is HDF5? If you're in a subject field, you may have encountered this as kind of the annoying data format that you may have to work with. It is rather ubiquitous now. You can find it through H5Py in Python or even built into MATLAB. If you use the newest version of .mat files, you'll find that it's actually that mat file is actually an HDF5 file itself. I realized over time that it's actually three separate manifestations, a trinity of things. It's a file format itself, and there's the open specification that you can go look up. It's also a C library and the C API, and it's a data model as well. And I think trying to approach HDF5 means really having to address each of these three things simultaneously. Although you can occasionally try to attack it from one of these manifestations of HDF5. So when we use HDF5, I think it's really good when you're storing n-dimensional data and you need attributes, you need to annotate it. So I think it fits really well with Julia and scientific computing. And you especially want to use it when you want to compactly store binary data. This is maybe as opposed to storing everything in XML or JSON, where you would have to write out the data into ASCII, and then they would have to retranslate it back into actually machine-readable bits and bytes. When don't you want to use HDF5? Well, variable length strings are a bit challenging in HDF5, as I think they are in any data format. So we don't usually recommend that, but if you know the length of your strings or your variable length data, you could use fixed length versions of those instead. The other thing that we don't really recommend you use with HDF5 is for tables, basically 2D heterogeneous arrays. You can kind of use it, and there may be some things coming down the line from HDF group and others when you want to, and in that case, you want to use columnar layouts and other things. But we'll have discussion with that at the data burst of a feather meeting. What are some related formats? I mentioned mat files earlier. NetCDF is being used in the geosciences community for things that like Simon just mentioned earlier. PyTables actually uses HDF5 for its table implementation, and you might use that if you're using Python, using pandas for data frames, even though kind of it's just that might not be the most optimal thing. And we're also using it as part of the JLD and JLD.2 ecosystems. JLD actually depends on the HDF5.jl and the C library, whereas JLD2 is actually an independent Julia implementation. I mentioned the specification. This is what it looks like. Not a lot of people maybe directly look at it. It's some people joke that it's a big book of things, and it's not too bad. I can show you a little bit later if you'd like to look at it, how we kind of work with this. But basically, my point here is that it's an open specification. You can go look it up, and it's not opaque, although perhaps complex. What is HDF5.jl? So primarily, HDF5.jl is a wrapper around the HDF group's C library. And we provide a direct one-to-one mapping via a low-level interface. This is the HDF5.API module. We also provide a mid-level interface, which is a very lightweight wrapper around those one-to-one mappings, where we do things like, instead of returning just error code, we will return the thing that you're actually trying to get. And so we take care of some of that for you. And then we also provide a high-level interface, a more Julian API. Sorry, I think I covered some of that earlier. That was a kind of duplication. So as I mentioned, I'm not the one who did all of this. Many have come before me. I think Connor Hinton was the first to maybe suggest that we build support for HDF5 in Julia. Tim Holey, Sam Kornblith did a lot of the initial design work, and we have had many, many contributors. Feel free to open a pull request. To this presentation itself, I accepted a change 5 minutes ago in order to correct some names. So if you find a problem or something you think could be better, please come by to HDF5.jl, create an issue, and create a pull request. So who's working on it now? I mentioned kind of my 3 co-presenters here. Mustafa is really the lead maintainer. He not only maintains HDF5.jl, but also a lot of the related packages, such as JLD and MATLAB.jl. Simon, who just spoke, is also a major contributor as he uses this in many of his projects at Klima. I've been kind of working on expanding API coverage so we could use all the HDF5 features efficiently. Especially, I'm thinking about chunking and how can we get to the data more directly and more easily. Simon's been working on kind of reorganizing the package, making it look a little bit more professional. We've done a lot of work with formatting and so forth. We've refurbished the filter interface so it's now modular and more extensible. And I think Simon will talk about virtual data sets and parallelization at the end of this talk. We also want to especially mention Eric for building HDF5 JLL. He's done a crazy, amazing amount of work to work on cross-compilation, resulting in about 192 artifacts across different C++ standard libraries, Fortran standard libraries, MPI versions. It's just an incredible amount of work. So much so that I think the HDF group took notice and reformed how they did cross-compilation in their library. So we're also kind of having a major effect from upstream. I think Julia is a really interesting language to wrap around HDF5.jl. HDF5 itself is a C library, and there's a lot of interfaces that uses things like void pointers, and you have to kind of cast things to itself. And so I think many people like the C++ API because it has some knowledge of types and things like this. But also other people like the H5Py interface because it's very dynamic and you don't have to think about types that much. And I think Julia actually brings together the best of both worlds. We can dynamically create types, we can do name tuples, we can read existing types structs that you create in Julia, and serialize that into HDF5. We can use reflection to learn about types that you created. And basically create corresponding HDF5 types. I think that's another thing that I really like about HDF5 is that it has a type system itself, and we can do a lot of things to map between Julia types and the HDF5 types. And I'll show you a little bit about that in a few slides. You can easily extend HDF5.jl for your types using multiple dispatch, and this is something that JLD in particular does. So in HDF5.jl, we're trying to stay pretty generic. But JLD provides more specific Julia bindings for Julia. Importantly, something that I found in also doing H5Py development is that we don't need this extra Python layer, and we can talk a little bit more naturally to C. We can interact efficiently with the library because we can do things like use callbacks for iterating over objects in the H5 library. Whereas this is a little bit more annoying on the Python side. And finally, I think we can also really efficiently bind calls in the C library. So I partially automated this already using clang.jl. And traditionally, this has been kind of just done by hand. But basically, with clang.jl, we can parse the HDF5 header and automate generation of these bindings. So how do you use HDF5? This is what basic usage looks like. On the top, we're writing an HDF5 file. Basically, we use an open with the do interface. And here, I'm kind of showing out the hierarchical nature of HDF5 because we can do nested groups and we can save an array. We're trying to keep this simple and maybe use natural array indexing, although I think we have a little bit more work to do to get there. And as I promised earlier, you can also store attributes, so you can annotate individual groups or arrays in HDF5. And then reading a file is pretty similar. In this case, we're printing back out the access state, and you can also use implicit return to return an array and get an array out of HDF5. I think one kind of cute feature that I like, that this was not implemented by me, I think it was implemented by Tim, was using emojis to kind of print out the hierarchy. So basically, you can see we use the root and folders and attributes. So you can see the tag is actually an attribute, and the numbers is an array. And I think that's a really nice feature to use in the REPL to kind of quickly understand what are the contents of an HDF5 file. And then, outside the DataSets, we can access the array. You'll get the data that we just stored in a previous slide. But when you do it like this, you have to make sure to close out the file. Otherwise, I think at exit, Julia and HDF5 will be really unhappy. So I mentioned the types, structs, and reflection. This is kind of just showing off how that works. In this case, I've declared a Julia struct, and then I have asked the HDF5.jl to now turn that into a corresponding HDF5 data type. And you can see what it's done is now created a compound data type with little endian corresponding integers or floats at the specified offsets and names. The HDF5 kind of type system is a little bit more specific in some cases. You can see it stores any in this. It also specifies, are we using standard floats or some weird floats or IEEE floats. And I guess the other thing I wanted to say about that is that HDF5 library will also do some translation for you if you basically specify that I want to read little endian, even though the data is stored in big endian. To kind of read and write that, this is a relatively new feature that's been iterated on through a number of contributors. But naively, HDF5 doesn't know necessarily what type you want to read into. And so when it doesn't know that, it will just read into a name tuple. But you can also specify the type you want and read directly into your structs. It's a little bit awkward to save scalars occasionally. So in this case, I'm just showing that we just have a one element array. Something that I think we've done a lot of work on in recent versions of HDF5.jl is to work on chunking and also compression. So in .116, we started reforming the chunk interfaces and the filter interfaces. This is, I think, again, work by Simon. So here, what we've done is we said we want to create a new data set. In this case, I'm just calling that data set GSub data. It's going to have a UNA type. It's going to be a 16 by 16 array. And actually, this is a little bit superfluous because you can actually just specify, just provide an array, and it would actually create and write it. But I'm just spelling this out for you. In this case, though, I've specified I want to chunk this into 4 by 4 chunks. So basically, each 4 by 4 point chunk will be contiguous in memory. This allows you to quickly access a subarray within the file easily. And this is more maybe not too critical for a 16 by 16 array, but if you have very large arrays, very high dimensional data sets, this becomes super critical. The other thing I've done here is I've specified I want to use GSIP, or in HDF5 called deflate. And so we're specified a deflate filter. You can see that's a vector, and that's because HDF5 supports filter pipelines. So basically you can string together a series of transformations, including compression. This could be useful if you have certain data sets that may be compressed better by either shuffling in bytes or maybe shifting the data around through some offset or some scaling. The last thing here is alloc time early. By default, if you just create a data set, HDF5 will not allocate the space in the file. So, but in this case, I said I want to allocate that space now. Part of the reason I do that is sometimes I want to write data into the HDF5 file without the library. I want to know where the chunks are going to be, so I can do that. We've worked on compression filter plugins recently. A big hint that we got was from Stephen G. Johnson, an MIT professor here, where he implemented the filter for BLOSK using his BLOSK.jl package. BLOSK is a meta compressor. And that provides a lot of compression capability from the get-go. Interestingly, this plugin is implemented in Julia. Normally, you would have to write a small piece of C code to kind of connect HDF5 with compression libraries, but in the Julia case, we could do that perfectly fine because we can create functions that are callable from C. So building upon that approach, we've now expanded this out to connect to C standard, LC4, bzip2, and bit shuffle. And frankly, if you have the compressor library in binary builder, the Agricel, we can very easily connect that to HDF5. And we can work on also kind of registering with the HDF group so other people know what we're doing. Something I really want to work on here is connecting this to JLD2. As I said, this is all Julia code, and so we should be able to abstract this interface out and make this available to JLD2, which will allow us to do to save Julia files using all Julia code and maybe some C compression libraries directly without having to depend on the HDF5C library. Importantly, as I'll mention in a few minutes, basically HDF5C library does enough for concurrent operation sub through MPI. This will allow us to possibly use multi-threading to do parallelization more easily. And so this is what using those looks like. Instead of specifying a built-in filter, I've now brought in a filter that's defined in the H5C C standard package. And basically, you can see that we just put that into the filters field there. Something that's pretty new that I think I need to start thinking about how we're going to integrate is possibly using a package extension to automatically load this when you load, say, codec C standard.jl. One approach for that might be doing it like we do these external filters here. So in this case, for an external filter, what I mean is you have a dynamic library that you're loading. So the plugin itself, the compression plugin is implemented in C. You're just trying to load that through the HDF5 library rather than using one of our Julia-based things. And in that case, all you have to do is specify the filter ID and just ask HDF5 to do it. HDF5 also has a mechanism to kind of say that I couldn't do it and just fail, but where it'll kind of indicate the state of the data in that case. But this means that you have a multitude of options to use external codecs or internal codecs for that matter. And this is a little bit of an advanced topic, I think. I think this is something that starting to differentiate us from H5Py. So HDF5 has a number of different interfaces to access objects. Often there are things like get chunk info, where you have to specify chunk 1, chunk 2, well, chunk 0. Or they have iteration methods, which uses C callbacks. And it turns out using the callback methods are really important when you want to get all the chunks or all the information for all the objects in a file. And I usually do this with chunks, so that's why I'm showing this. But the iteration methods scale really well, whereas the index-based methods that Python tends to use in H5Py don't scale that well at all. You can see that once we get up to about 10,000 chunks, the difference, the ratio of performance is about 200-fold. So one thing to note is that the C API doesn't allow for multi-threaded concurrency. Basically, one method to get to kind of use threads with H5 library is to have the C library install locks. Instead, in HDF5.jl, we've applied our own lock on our side so that we can more efficiently manage that. And so that's basically surrounding all the calls. And so you can use H5.jl with multi-threading, and it should be thread safe. I think we're still occasionally finding a bug or two, but if you do, please let us know. But I think this is in a much better state for multi-threading these days. Okay, I'm going to turn it back over to Simon, as I promised, to finish the Simon hour.
Thank you. So virtual data sets are an convenient way of splitting up data into multiple files. I actually went through the HDF5 spec once. There are 7 different ways to split up HDF5 into multiple files. None of them make any sense except for this one. So virtual datasets, basically you can write each HDF5 slice, like a chunk of HDF5 to a single file, HDF5 file, and then virtual datasets let you look at. You can create a dataset, which is basically a view made up of all these little chunks, which can be either the same file or completely different files. And actually, what's really nice is it handles patterns. So you can have, if you don't know how many files there are going to be, it will just keep extending the array based on what file pattern it sees on disk. So this is really useful for us where we're writing out data files over time. We don't know when we'll finish, or if it crashes, you want to still give you something useful. Stops early, so it'll just give you an array of however many big you want. Yeah, so and that took a little bit of effort. They're still not super happy with the interface, but it's not too bad to use, and it takes a bit of practice. I still don't quite understand all the pieces, what options there, but we'll try and improve this as we get there. The other piece I spent a bit of time on was parallelization via MPI. So this, again, I'm very thankful to Eric for getting the binaries built that support MPI. So MPI, for anyone who's never used it, is basically an interface for single program multiple data parallelism. So what that means is you launch a bunch of copies of a single program, which all sort of communicate with each other individually. So you say, I want to use 10 processes and launch 10 copies of the same program, and they'll go, I'm process 1, I'm process 3, oh, I should talk to you, you talk to me, and send messages. It also provides an I/O interface, and so HDF5 can use that I/O interface to basically so multiple processes can safely write to the same file. And so how this works is basically you load MPI and HDF5 and you initialize MPI.init. And then in H5 open, we can pass this extra object called a communicator. So a communicator is like the sort of shared representation of multiple processes. And so this has to be done collectively. So all processes have to open the same file at the same time. In particular, you need to make sure that file is accessible from all the processes. So if you're doing distributed work, you have to use a shared file system. Otherwise, unfortunately, it will just stop and not tell you anything. You'll just hang. No errors, just hang silently. So that's careful. But otherwise, it's basically once you've opened the file, it's basically the same as normal. The only main constraints are that sort of the metadata operations, so like creating a data set, writing attributes, have to be all done collectively. So that means all processes have to be doing them at the same time, or like in the same order, really. Not exactly the same time, but same order, with the same arguments. So you have to create the data set. All processes have to call create data set. But then when you're actually reading and writing data, that can be done completely independently. So process 1 can write to one chunk, process 2 can write to a completely different data set, or whatever. But that bit is done independently. The main thing for performance reasons, you tend to want to align, if you're using chunks, you want to align those with the process boundaries. It doesn't have to, but you'll get better performance. And there's this option called collective, which basically says, if you know all the processes are going to be writing at the same time, you can use this option, which may give better performance. Couldn't tell you. There's a few limitations, so you can't use variable length strings in data sets, for example. So like anything where it has to use adaptive memory. So it has to sort of be able to pre-allocate a bunch of the space up front. And configuring HDF5. So we do provide an option now to we're hooked into the preferences system for if you want to use a custom MPI HDF5 binary. So there's a few reasons you might want to do this if you're using MPI and you're linked against a custom MPI binary. Interoperability, if you want to use the same one as Python users, for example, or if you have very, very fancy hardware and they built it to use, so HDF5 has all these nice layers. It can support things like burst buffers and things which are on big HPC systems. We'll handle this for you. So it can take advantage of that. And so preferences, it provides a mechanism where we can just say use this binary or use these. These are the two libraries we end up using. So you have to use both of those. So it's used in quite a few applications. So I mentioned Klima, we use it. Checkpointing.jl is another different package for HPC style checkpointing for adjoint mode automatic differentiation. Because the idea is you need to be able to write the files and then go back, write data over time, and then you need to go backwards. And so you use it as a checkpointing. Plots has a backend, and JLD2, as we mentioned, and JLD and JLD2. Mark, did you? Sorry.
Yeah, sorry. This is kind of where this is a hybrid slide that Simon and I made. So basically JLD is a direct dependency, so it's MATLAB.jl, and JLD2, as I said, is an independent implementation in Julia. It's kind of a really rare thing actually, but it does use HDF5 as a reference to make sure that files it writes can also be read by HDF5, so it can be used in different languages. So basically, that's it. That's the summary. Basically, this is a wrapper around a C library. HDF5 itself has different things that you can think about it as, in terms of format being a library itself and a data model. And we've done a lot of work on different aspects, filters, multi-threading, and other capabilities that make it work better in a Julia environment. And Simon has himself done a lot of work with MPI and to make this work for true parallelization. So, do you have any questions? Please let us know.
Stefan.
Now that HDF5 has sort of got more features and more work is being done on it, does that sort of take away some of the reasons that HDF5 or JLD2 was implemented? I kind of remember when there were like deficiencies with the C library.
Yeah, so JLD2. So the question is, does HDF5, now that HDF5 have added a bunch of features, does that sort of negate the need for JLD2? Maybe. I mean, I think the big difference. So JLD2, I think, is since Simon stopped maintaining it, I'm not sure if it's has a sort of standard maintainer now. So it's sort of people patch it occasionally, and so that's one reason. It tries to be a bit clever about it tries to auto serialize Julia types and handle a bunch of other stuff, which HDF5.jl doesn't at all. We intentionally tried to keep it. You have to manage that stuff yourself because there is still a lot of issues with when you try to reload types that if you haven't defined them already, I think that still causes problems. JLD does some fancy things like with memory. It does a bunch of stuff using memory mapping and then I think may work with threading. I'm not sure, but actually the memory mapping causes us all sorts of problems because people try to write. If you can't always memory map, if I'm on a shared file system, that will go terribly. Yeah, so it's pros and cons. Yeah.
And I think it's also nice to have an independent implementation of HDF5. There are not a lot of those out there. In particular, the HDF5 C library is 25 years old, and it has maintained full backwards compatibility over that lifetime. And so there's a lot of legacy that they have to deal with. By being an independent implementation, I think JLD2 has a chance to maybe get to actual concurrent multi-threading with the HDF5 files, maybe even before HDF group does. And so it's a bit of a race. And as I'm learning more about HDF5, I'm thinking about how can we bring that knowledge to JLD2.
And one option is to combine the two, is to use the HDF5 library for some things and then just have our own specific implementation for other things. That's some sort of hybrid option there as well. Yes.
Are you aware of any work on using lossy data compression methods?
Sorry, I can't quite hear you.
Are you able to plug in lossy data compression methods into your pipeline?
So the HDF5 library does have this plugin architecture for filters, including compression.
And lossy, it does support lossy ones, yes.
And it does, and some of those compression algorithms are lossy. Actually, my own institution has this thing called HDF5J, which incorporates I think the H.265 codec to store arrays, although it doesn't really correctly use the filter algorithm, something I'm working on. But yes, and if you have one yourself, it's pretty easy to plug in. We can do it completely in Julia if you would like.
So the question is, compare it with, say, Apache Arrow. I would say, I think we tried to cover that earlier, but Apache Arrow is like trying to be a tabular format for tabular heterogeneous data. You have tables of different columns. Is that a good summary? HDF5 is really, you can use it for other things, but it's really focused on numeric data. I'm going to be honest. You probably don't want to use it for strings. And it's really powerful for multi-dimensional arrays. I guess are the two big differentiators. Yes, homogeneous arrays of homogeneous data. Sorry, can you repeat that? So if you want to like store a dictionary, I mean, you could. I mean, it sort of is like it provides this group structure, which I guess itself is a dictionary. So if you only have a small numbers, you can use the its sort of tree hierarchy as a dictionary, which is why that's how we provide the interface. But if you want to like serialize a huge dictionary, it's probably like you'd have to. No, I mean, it doesn't have a way to like store lookup. It doesn't expose like a B tree, like a tree interface or anything that you would want to say, okay, I have tree data, like that sort of thing.
I guess I'll say one other thing about that is that Arrow is meant as a kind of in-memory file format for IPC. So it doesn't necessarily pack the data structure completely, whereas HDF5 is meant a little bit more for persistent file storage. And so there's a little bit of difference between those formats. But there are other things like Parquet and things like that that I think maybe we'll discuss at the data BOF. Okay, I saw one more question up there. Yes, please.
Compressor for large numerical arrays.
The question was, is there a good compressor for large numerical arrays? And so I think this is a $1 billion question. In my experience, it's hard to find a generic compressor. So what you maybe to qualify your question is like, are you using floats? Are you using ints? I think a good compressor to start with that I found recently is using C standard. Basically, anything I've thrown at that, it's done pretty efficiently and compressed pretty well, although not necessarily either the fastest or most compression ratio. Do you have any other thoughts?
I actually have very little experience. But I was going to say there are one of the plugins. There's actually a whole like class of like lossy ones that are specialized for floats. Where they'll like try and normalize them within the chunk, and then chop off the trailing bits so that they're trying, basically, actually not dissimilar like how quantization is used in machine learning, and these sorts of So there's actually a lot of custom ones that people develop for very specific applications. So, answer is.
At Livermore called ZFP, and there's one at Argonne called SZ.
I missed. I can't quite hear the names, but yes, there's. Yeah, Argonne and Livermore both have their own specific compression algorithms.
Okay, so we can probably have just one more question before we wrap up because we're already running out of time.
Michael, go ahead.
Sorry.
It is critical. So the question is, how important is it to use fixed length elements? And I think this is critical because, so the problem here is if it's variable length, right, you don't necessarily know where the nth element is going to be. You have to kind of start reading through the entire data set. And so I really highly recommend using fixed length elements, fixed length strings. To support that sort of strings, I'm implementing a package called static strings.jl. There's also inline strings.jl that helps with this. But yeah, I think it's really important. It really would improve performance if you use fixed length elements.
Yeah, I think the HDF5 format maintains its own like heap for sort of variable length objects, and then so if you have variable length objects, do that. If you have fixed length objects, it just does them in place.
Okay, thank you.
Thank you very much. Let's go ahead together.